Hello everyone, welcome back. Today I'm going to cover section 14.5. I'll be talking about a chain rule, multivariable function, and as usual I'll try to link back to one variable function that you guys learned in Cat 1. Say, recall you have what? Y equal to f of x, right? And now x is not a variable. X is a function of t, so let me write it this way. Okay? So you want to differentiate y respect to t, right this way, dy over dt. I'm using a left notation. Is equal to what? Dy over dx times dx over dt. Oh, let's say dt. Okay? In other words, you want to differentiate y, right? You take the derivative of the function fx, but now x is not a variable. X is a function with respect to t, so you have to multiply by x prime of t. So really, y prime is f prime of x times x prime of t. That was what you guys learned in Cat 1, right? This is what it means right here, dy. But this is kind of cumbersome because if you write y prime, you don't know the variable that you're taking derivative. That's why left notation looks better. dy over dt, derivative of change of y respect to t equal to change of y respect to x times change of x respect to t. Kind of cancel out the x right there. Okay? That was the chain rule in one variable. And it pretty much carry over to multivariable, but just have some chance because you have more than one variable. So many times, you have to use partial derivative. So first case, two cases, okay? So case number one, you have the function z equal to f x comma y, where x is a function of one variable t, and then y is another function of one variable t. Okay? So you calculate z in respect to t, and I'm going to use limit notation. So dz over dt will be equal to fx, or dz over dx. You remember that notation, right? This is derivative respect to partial derivative respect to x. Okay, I'll write this way. It's the same thing. Okay, dz over dx times dx over dt. Now with x, I'm using like regular d because what? Just one variable, it's not a t. Plus dz over dy times dy over dt. Okay, this is the formula for calculate derivative with respect to t. And similarly, you've got z equals to what? Xy and then st, where or xy, st is a variable t, and then you just add more dz over dx, dz over dt. Okay, that's it. Same way. Example. Say I got z is equal to x squared y. Make it easy. Where x equal to cosine t, and y is equal to sine t. So, one way you can calculate the derivative in terms of t, the derivative of z with respect to t, without doing a chain rule. You just simply look at x equal to cosine t and y equal to sine t in here. Then you can differentiate directly. And this is what I mean. So with this example right here, you can look at z is equal to cosine squared t times sine t, and now you calculate dz over dt directly. It becomes a function of one variable, z in terms of t. And you have to use what I think derivative of trig function, and then product rule, and then chain rules in here. Okay, and this is for you. I'm trying to use in the chain rules that we have from two variable functions. So I'm gonna use a formula right here. If I got z is equal to x squared y, then dz over dx is 2xy, which is 2xy is 2 cosine t sine t, and dz over dy, my d looks ugly, so over dy is dz over dy is x squared. X squared is cosine squared t. Now you calculate what? Dx over dt. Dx over dt, derivative of cosine is negative sine t, and dy over dt, this is my comma. Okay, dy over dt is what? Cosine t. Now you put them all together. with this example right here, dz over dt will be equal to dx, dz over dx, which is this one right here, 2 cosine t sine t times dx over dt, which is cosine t, okay, plus, dx is negative sine t. I make a mistake right here. So, times negative sine t. I say dx over dt, but I look at dy over dt. And then plus dz over dy right here, partial derivative dz over dy is cosine squared t times dy over dt is cosine t. And of course, simplify, you have the answer. It's going to be negative 2 cosine t sine squared t plus cosine cube of t. That would be dz over dt, okay, using the chain rule. And of course, if you don't want to use the chain rule, you can differentiate z from here directly. You should have the answer. Now I wonder what answer should I have, so let me do it. Okay. You see what we're talking about right here? I use a function z equal to x squared times y, where x is cosine, so x squared cosine squared, and then y is sine t. I plug in. So I change from the function of two variables x, y into a function of just one variable t, and then I differentiate using count one. Okay? So dz over dt. I'm going to use product root, the root of the first times the second. The root of cosine squared is 2 cosine t times negative sine t. I'm using power root 2 out, so 2 cosine t. And then chain rule, the root of cosine is negative sine. The root of the first times sine t, that's the second, plus the root of the second point, the root of the sine is cosine t times the first point, which is cosine squared t. I got the same answer. Okay, that works. And that's the first case where multivariable function, each variable is a function of the same variable t. You can do that. Okay? And let me generalize it a little bit before I move on. So you guys have a general picture of it. So in general, say you have a function f of x1, x2, x3, or how about x, y, st or something. X, y, st, or maybe more, okay? Say z equals to that. Doesn't matter how many variables you have. I should not use t. T is a variable, so x, y, s, how about w? Where x is a function of t, y is a function of t, s is a function of t, and w is a function of t. All of those variables of the function f are actually another function of the same variable t. So dz over dt, same way. You have what? dz over dx times dx over dt. See? Partial root with respect to x times the root of x, chain rule. Okay, and then what? dz over dy times dy over dt. Same idea, change to the y. And then move on, dz over ds times ds over dt. And then the last one, dz over dw times dw over dt. And you have another one. Right? And here I give you a little bit more general 4 variables. You have the same way if you have 5, 6, 7, 8, 9, 10, 1,000 variables. It just works the same way. That's case 1. Now let me move on to case 2. Let's start with function of 2 variables, z equal to f of xy, okay? Now, x is not just a function of one variable. X is a function of 2 variables, u comma v. And then y is another function of 2 variables, u comma v again. Maybe 2, maybe 3, doesn't matter. Okay, now we want to calculate the root of z. We don't talk about a single variable derivative anymore. We're going to talk about what? Partial derivative, because z now is going to be a function of 2 variables, u and v. Because x is in terms of u and v, y is in terms of u and v. So technically, z is in terms of u and v. So I think before I give you the formula, I should give you an example of the function just to demonstrate it. Say I got z is equal to x squared plus 2xy. Try to make myself easy, okay? Where x equal to u plus v and y is equal to u minus 2v. Okay? So you see that x itself is a function of two variables, y, u and v. And y is also another function of two variables, u and v. So really, you can plug in x equal to u plus v and then y equal to u minus 2v, and you can differentiate right away. You can have z is equal to what? U plus v squared plus 2 times u plus v times u minus 2v. You see that z right here is really a function of u and v, right? Two variables. See, because x is in terms of u and v, and y is also in terms of u and v. You substitute x and y by function of u and v, you really have z in terms of u and v. And now z is a function of two new variables, u and v. You can calculate what? Du over dz over du, I mean. dz over du, then you can calculate dz over dv. Differentiate it. Of course, we're going to multiply them all out and then simplify. Okay? But now, we're going to use the chain rule so we don't have to do all the algebra work, that much algebra work, and hopefully it's faster. And the formula is this. Let me keep the example right here. I'm going to write a formula right here. du, keep writing dz over du is equal to dz over df times dx over du. You guys see, pay attention to the notation right here. I don't write the straight d anymore. It's going to be partial derivative of x w, because now x is function of two variables. Plus dz over dy times dy over du. Okay? Now I got dz over du. Similarly, I want to differentiate function z with respect to v. Partial derivative of z with respect to v. It's going to be dz over dx times dx over dv. See? Because in here, the same way, just replace u by v. Okay? The original function is variables x, so differentiate with respect to x, and then time the function x with respect to v. I got dz over dv. And plus dz over dy times dy over dv. And I have dz over dv. Okay, let's work with this example right here. See what you got. I got z equal to x squared plus 2xy. So dz over dx is equal to 2x plus 2y. And dz over dy, this one is 0, dz over dy is 2x. Okay? Now I got x equal to u plus v, so dx over du is 1. Because what? U derivative, so let's use 1, v now 0. dx over dv, dx over, excuse me, it's still 1. And then similarly, dy over du, dy over du is 1. How about dy over dv? It's going to be, this is my v, okay? It's going to be negative 2 right here. So after having all the partial differential, you're going to plug into the formula. You should have the answer. Okay? Sorry, guys, I have to erase because I need some room to write. So, I want to calculate dz over du. Come in. dz over dx. dz over dx is 2x plus 2y times dx over du. dx over du is 1 plus dz over dy. dz over dy is 2x times dy over du. dy over du is 1. And of course, go ahead and simplify. Okay? And keep in mind that x is what? U plus v, and y is u minus 2v, you plug them in. Right? A little bit more, but this is the idea. Similarly, you want to calculate dz over dv. You do exactly the same thing, but using this line right here. dz over df, dz over df is 2x plus 2y. And then time, right here, right? dx over dv. dx over dv is 1 plus dz over dy. dz over dy is 2x times what? dy over dv right here times -2. And then after that, you simplify, multiply, combine the like terms, all the algebra. Okay, you should have the answer. This is the main idea. So in here, I'm showing you the chain rules for a multivariable function, and you guys see the rules. Let's see if I missed anything. Oh, how about we generalize it? What if we have a function f of like 3, 4, 5 variables, and then each variable is another multivariable function, and the idea is the same. So let me show you. F of, say, x1, x2, x3, x4. You can have x5, x6, okay? So I'm trying to show you a more general case of a multivariable function. In this particular example, I got a function f of 4 variables, x1, x2, x3, x4, right? So I won't confuse the other letters, just count 1, 2, 3, 4, okay? Where x1 is a function of, say, 3 variables, say t1, t2, t3, okay? Of course, y, x2, there's no y here. x2 is also another function of 3 variables, t1, t2, t3, then x3 is also t1, t2, t3, function of 3 variables. And then x4 is also another function of 3 variables, t1, t2, t3. You see what? A function f of 4 variables, x1, x2, x3, x4, where each variable x is another function of another 3 variables. Okay. And the idea is pretty much the same. You just do more work because you got more variables. So if you plug in x1 as a function of 3 variables, t1, t2, t3, x2 another t1, t2, t3, x4, x3, x4, the same thing. It turns out that what the function f is really the function of 3 variables, t1, t2, t3. Okay, because x is really t1, t2, t3. Same thing for other x. Okay, so you want to calculate, say, the derivative function in terms of dt1 respect to the variable 1 as well. You got a partial, you do the partial derivative for each of the variable right here. So df over dx1. Now you have to multiply d is x1 over dt1. You see, make sure that you can, when you cancel out the dx1, you got df over dt1. And then you do the same thing for the other variables. Plus I have some room right here. Plus df over dx2 times dx2 over dt2. Oh, t1, I mean, all 1. And then df over the x3 times dx3 over dt1 plus df over dx4 times dx4 over dt1. Make sure that we calculate df or dt1, right? So for each of those terms right here, whenever you cancel out the intermediate variable, make sure that you got df or dt1 all the time. Good. Similarly, if you want to calculate df over dt2, and everything right here change to 2. The t change to 2. The x stay the same. Okay. Partial derivative with respect to x. Derivative x over t2, that's derivative x2, x2 over t2, so forth and so on. And it's just example, but in general, you can have what? 5, 6, 7, 8, 9, 10 variables, and each variable is a function of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 variables. You do the same way. It's just more work because you have to do more calculation with more variables. And that's it. You should have the formula for the chain rules of partial derivative for each of the variables. And And this is the end of 14.5. So, and I see that the homework in this section is just, I think in my opinion, okay, it's routine. Just check for your skill of taking the root. Be very careful with your calculation, but it's not too hard. But as usual, again, any question, please feel free to ask. I'll try my best to answer your question as soon as I can. And I will stop the video right here. Thank you for watching, guys. Have a good day.